So we've just now done the dot product, and we said the dot product between two vectors A and B is just the magnitude of A times the magnitude of B times the cosine of the angle between them. But just a few minutes ago, we defined the work done by a force is equals to the magnitude of the force times the magnitude of the displacement of an object times the cosine of the angle between them. Right? If you think back a few minutes ago, that's just what we said for work. Basically means the component of this force that's parallel to the displacement, that's the component that's actually causing acceleration, causing a transfer of energy. So we can write work actually as the dot product of force times, displacement. So the dot product of these two vectors. All right, because we know how this scalar product is defined. Now let's look at a special case. Let's assume the force is applied parallel to the direction of motion, so it's applied parallel to the displacement. And let's say the magnitude of the force is constant. So the force does not become stronger and stronger and stronger, or weaker and weaker and weaker. It just remains the same. So what this means is, if I were to draw a graph of the force and the position of whatever object it's acting on, let's just get ourselves a picture. Let's say that's a box. This force is being applied in that direction, and it causes a displacement like that. Let's say this box started at x initial is equals to 0, and it then is displaced to a certain point, x final. So if I want to plot the position, on the one axis I've got the position of this box, on the other axis I've got the magnitude of the force. So when this box is at position xi is equals to 0, the force has got a certain magnitude. We said the force remains constant, so when the box is over there, over there, over there, over there, the magnitude of the force is the same at all those positions. So when the box is over there, over there, over there, over there, the force has got exactly the same magnitude throughout. And let's say the box ended up over there. So the box started from here, it ended up over there. So force as a function of displacement is just that straight line that I've drawn. And let's have a look at what's given by the area under this curve. So what's given by this area? Yeah, just the work. This area, let's call this area A. So this area is just equals to the magnitude of the force times the change in position, which in this case is the displacement. This, we said the force is parallel to the displacement, so we don't have to worry about cosines and things like that. And this is just equals to the work done by this force F. But we're not always going to be this lucky. So we're not always going to have a force that is constant. I just want to get this. Go. And here is a very good example of a force that is not constant with position. If you read this, this is essentially a force meter. So this yellow little plunger at the end tells me how much force I'm applying. Right over there is 0. There is 2 newtons, 3 newtons. So as I'm pulling on the end of the spring, the further I pull the spring out, the larger the force is that I must apply to pull it further. So clearly over here, I have to apply a negligibly small force to cause a small displacement. But the further this thing is displaced, the larger the force that I apply must be to keep the piston going. So a spring is a very nice example of a force that is not constant as with change in position. So how do we calculate the work done then by a force that changes its magnitude as an object is displaced? So what we want is the work done by a variable force. So let's just draw some graph. This will again be my displacement. This will be the magnitude of the force. Let's assume at least the direction of the force is always parallel to the displacement, so we don't have to worry about that. But the magnitude of the force now changes. So it's not necessarily going to be a spring. Let's just look at a very general case. Let's say for whatever reason the force increases with increasing displacement and then starts to decrease with increasing displacement. So for whatever physical reason, I'm applying a force to an object, and initially the force increases as the object is displaced, and then the force decreases as the object is displaced. So this force obviously is not constant. So how can we now calculate the work done by this force? So if we think about the previous graph, we had, okay, well, the work done by a force is equals to the area underneath the graph. So let's say our object started over here, and let's say our object ended up at a position x final. So the area that is enclosed by the graph between x initial and x final should give us the work done by the force. And we can calculate that. We can start to approximate it. Let's look at a small segment. Over there the curvature is very little. So if we were to look at a very small section, so we're looking at a tiny displacement delta x. And if I were to zoom in on that, I would find that the force, the magnitude of the force doesn't change a lot over this interval. So the force is approximately constant for this tiny interval. And I know how to calculate the work done by a constant force. That's just going to be the area of that rectangle. So the work done in moving the object through a displacement equals to that tiny interval. Let's call that, so let's just give this a name. Let's say over there we had, let's just call it x, some value of x. So that's in the middle of that rectangle. I'm just going to call it xn for now. So the value of the force over this interval is approximately equals to that. Right? The force is some function of x. If we know x and we plug it into our formula, whatever that might be, out comes the magnitude of the force for that position. So the work done in moving an object over this interval is just going to be equals to the magnitude of the force. Well, it's almost going to be that because the force is not constant, but if we choose this to be small enough, it's a good approximation. So whatever the magnitude of the force is at that point times the displacement. And we can now get a good approximation of the total area under the graph by just dividing the whole thing into little rectangles. And we choose the width of these rectangles to be so tiny that over that interval, the magnitude of the force doesn't change by a lot. So it's not an exact calculation yet, but it is at least a good approximation. So the total work is equals to the sum of all the areas of all these little rectangles, and we can give, if we can give the x coordinates names, that would be xn minus 1, let's call that xn minus 2, that would be xn plus 1, and so on. And we've now divided this area into a certain number of tiny little rectangles. So if we add them all together, it's the sum of all the areas of the rectangles. That's going to be equals to, each rectangle has got an area which is the force at a certain position times the magnitude of that interval, and that little index goes from 0 to, say, however many little rectangles we had. So what we're saying is we can get the total work done by adding up all these tiny little areas. Now, can you remember in tutorial 1 you did a similar calculation, right, where you had the velocity versus time, and you were asked to calculate how the area underneath that curve increases, or how the displacement, which is given by the area underneath that curve, increases as time goes on, right? And you found that for a straight line, like velocity versus time, the area underneath that curve increases as time squared. And we called that an integral. So what we say is this becomes exact, this expression, if we make, again, if we make these x's go to very, very small, so make these rectangles smaller and smaller and smaller, and the fancy way to write all of this is by that sign. That's called an integral of the force as a function of x times an infinitesimal little displacement all the way from some initial position to some final position. So this is, those of you who've not done this in calculus yet, this is called an integral. And what you need to know for now is this integral is always equals to the area under the curve f as a function of x between these two values. So between x initial and x final. So if you see an integral, you must think, okay, I must somehow calculate an area underneath the graph. Now, I'm just going to show you there are certain cases where calculating an integral is pretty simple. Basically, an integral is, roughly speaking, the reverse of differentiation. So if I've got, say, a function, let's say a is equals to x squared plus bx plus c, and I want to calculate the derivative with respect to x, let's say the function fx is equals to that, we would have that the derivative with respect to x, remember I showed you this little quick way of doing it. We basically take that number, put it in front, so it would be 2ax. That's actually exponent to the power 1. Put that in front, so it will be plus b. We have to decrease that by 1. So from 2 it goes to 1. From 1 it goes to 0. And the derivative of a constant, that would have been x to the power 0. Take that 0 to the front. 0 times anything will be 0. So the derivative of this function with respect to x is just 2 times ax plus b. Now the integral is the reverse of this. So if I want to calculate the integral now of this function, 2 times a times x plus b, and we always note the variable that we have to integrate with respect to at the end, this must be, so if I differentiate, I go from this function to that. Integration is the reverse. So if I integrate this function, I must get again ax squared plus bx plus a constant. So the integral is the reverse of derivative. But you should note that this constant is slightly problematic. If you now were to take the derivative, that can be anything, and you will get this expression. So an integral is specified up to a constant. That constant you need to determine from some other sort of condition. But luckily, we will be looking at things called definite integrals. And I'm just going to show you the formula for that. So let's look at a simple function. Let's say if x is ax plus b. Right, so simple straight line. And I want to calculate the integral now of this function. But I want to calculate it, remember integrals are areas under a curve, so I want to calculate it between two values of x. How we calculate this is, okay, I know that whatever I write over here, if I differentiate it, I must get this. So if I were to take a half times ax squared plus bx, if I were to take the derivative of this with respect to x, I would just end up with that. Right, so the integral of this function is equals to that, but we want to evaluate this at 2 points. And this is now called a definite integral because we specify the values of x. And in mathematics, you will learn exactly why this is so. But if you see something like this, it basically means you substitute in x final, and you subtract from that exactly the same expression, but now with x initial substituted in, or whatever this lower limit was. Okay, so this is how you calculate a definite integral. Definite integral is always something with limits specified. So this means if that's f, that's x, that might be some function. If that's x initial, that's x final. It means this area A is equals to that integral. And the way to calculate it is if you know, okay, this is obviously not a straight line, but if you know f as a function of x, you can calculate the integral in this way by remembering that if you differentiate that expression, you must end up with the function that you're integrating.